Thank you so much, Boris, and good morning, everyone, and thanks for joining us today. It's great to come back to a Wood Solutions online event. So obviously, well, I used to be part of the podcast and also the webinar series back in COVID days when it just started. So it's really good to come full circle. So for today's presentation, we're going to be looking at the design of timber connections and covering a lot of ground in one sense, but also going into detail about how we can actually design some of these connections. So thanks everyone for joining today. So on the agenda, we're going to talk a little bit about the brief problem that we're trying to solve on our organisation as a timber engineering software company. We're going to look at the balancing of priorities when it comes to connection design, and then a worked example of specific connection details. So firstly, what are the problems that we're trying to solve at CLT Toolbox? So when you look at the status quo buildings like concrete buildings, there's a few things that are about it. One of it is it's easy to do, although it's sometimes less desirable for timber buildings. But when it comes to timber buildings, we notice that there's not as much education in undergraduate curriculums relative to concrete. There's a lot of building engineering spreadsheets and also maintaining spreadsheets. And there's a lot of going through PDF design guides and maintaining a lot of grades from the member design supply chain, but also the connections design supply chain, and also how those products interact with each other. So what we're looking to do is build tools to essentially make this pathway as easy as possible. And in doing so, if you make it easy for engineers, then hopefully we can support in growing the pie of timber, particularly going into new areas. So our platform, we build tools to enable profitable design of timber buildings. So anything that was previously a lot of time investment, we're hoping to make it easier and in essence, make it work. So we've got a team around the world, as Boris mentioned. We're a bit of an eclectic bunch, but we're all pretty all in on what we're doing as a team together in building this software. So before I go into it, I always have to thank the partners who are working with us at CLT Toolbox, make it, everything that we do possible. So thanks to all of our partners. All right, so for context setting, when it comes to connections at the baseline, what connections do is, a structure is a constructed assembly of joints separated by members. And this includes connections of anchors, screws, nails, dowels, bolts, brackets, plates, glue, timber, or a range of these things. Then you've got members, which could be floors, walls, beam, column, shear wall, bracing, cores, etc. And then you've got different materials, which could be CLT, glulam, LVL, light frame, plywood, concrete, and steel. So it's a mix of all these things, and a lot of that can create a lot of complexity when it comes to design, particularly being an anisotropic material. The second point is connections touch many disciplines that impact the successful design of a connection for a building. So what are the things that we need to consider when designing connections successfully, not just looking at the structural design? So we're going to cover a range of multidisciplinary topics here. And the first one accounts for design for manufacture and assembly. So a bit of a plug for another Wood Solutions webinar, which is presented by Nathan Benbow, and it's Getting DFMA Right. It's an excellent webinar, but the point is, for the same connection detail for a beam column connection, for example, there is a huge variation when it comes to CNC machining costs, because from a member supplier point of view, the CNC machine can be the bottleneck. And if you're looking at throughput at a factory, it might be, say, 100 meters cubed if there's no bottlenecks, or it might be 200, or it might be 50 meters cubed if there is bottlenecks. So that cost needs to get passed on in some way or another, and usually it's held up by the project. So with timber, we can always go complex as we want, but we need to consciously, I guess, engineer in the complexity and know when we're doing that and adding costs. So if this is a limiting factor of cost, how can we design with the design for manufacture in mind? And you can see some of the details, the real simple seated bearing connection, which they highlighted as basically the simplest to draw on paper, but also from a cost point of view. The second point is design for assembly. So if you think about that, when it comes to material supply price of timber versus, say, concrete, timber might cost more upfront, but the way we actually get to cost parity is through the speed of construction a lot of the time. And that way we can reduce our preliminary design cost of the building. But this isn't baked in. Just because you're designing in timber doesn't mean that's automatic. So you think about if the crane is the limiting factor to our installation speeds, which enables that speed, the hook times can vary based on connections. So how can you design a really quick to install connection just to keep the crane going on to the next one? You've also got structural design. So think about tolerances. You might have the moisture within the timber that's delivered on site. You might have rain events, things like that, to actually have swelling or shrinkage when it's in service. You might have elastic deformation, which is different parallel or perpendicular to grain. You might have deflection of the transfer structure. You got all of that happening within the timber structure. And if you're designing with connection details that might go to a concrete core or something like that, the differences in tolerances have a big impact on the overall connections, and also, I guess, the structural safety in service. We've also got durability. Are they designed properly for external weather conditions, or are they just internal connections? And of course, robustness. So that sometimes in a basic looking design of a building might actually govern a lot of the design to enable robustness. So what happens if you knock out one of these columns, and how does everything connect together so you don't have disproportionate collapse? You've also got different materials behave differently. So if you look at this connection, you could have steel to a CLT floor, and under a fire condition, the timber here would char and not reduce under, I guess, thermal conductivity of the heat throughout the timber. But steel, on the other hand, if it conducts the high temperatures through the steel and through the fixings here, you might have the combustion reaction beginning prematurely in the middle of the timber. So that's something to think about. We've also got fire design and compliance. So compliance is a big one. If you speak to a supplier and if they've got fire tests, then you might not have a challenge. But if you're designing a connection that's never been done before, there might be a hidden surprise toward the end of a project to get a fire test to have your connection compliant. So compliance is really critical, and also avoiding testing for that cost, but also something that might land as on the critical path of the project delivery. Of course, you've got seismic design. Timber elements are brittle. The steel elements are ductile. So getting a ductile connection is a big part of it. And looking further at compliance, there's also different design methods. So this is looking at structural engineering, and I will cover in a bit more detail in my work examples throughout the webinar. But for example, you might have AS 1720, which is well recognized in the building code. So you might get a tick there from a compliance point of view. But the other design methods might be more sophisticated and accurate, particularly when it comes to mass timber buildings. So for example, current Eurocode is the most mature design code globally when it comes to timber design, and it's the most used globally as well, with the most runs on the board. But then you've got the new Eurocode, which is the cutting edge version of the Eurocode. It's been less used, and it's in the final draft stages. So, should you actually be using that if it's covering gaps in the current Eurocode? And then you've got European technical approvals, which is a design approach which is very specific to the supplier's testing of their product. So you could argue that that's the most accurate way to design. But obviously, the final three are going to be performance-based design from the outset when it comes to mass timber. You've also got to think about keeping the supply chain options open, or understand the trade-offs for this. So if you choose, for example, one supplier up front, you're going to have one set of sizes, one set of grades and densities of the timber. And when you choose the screw supplier as well, in this instance, say for a spline joint here, you might design specifically to their ETA, which might be specific on a density, for example. But what happens if you change your properties? So XLAM, they've got the equivalent of MGP6 or their XLG2 in the middle, which is different to Next Timber. By Timberlink, they've got MGP10s, which is different to Red Stag. So they're all using pine. But then if you go to a European supplier using spruce, which has an entirely different density and different properties based on the species of timber. So what happens then compared to the screw suppliers? What happens if you change your supplier, or if a screw supplier, for example, runs out of capacity and needs to air freight it or something like that? So again, you don't need to know everything back to front, but it's understanding the benefits and costs of backing a horse as early as possible. So there's a lot going on with connections. It's more complex than probably any one individual can cover. There are people, of course, who go well beyond me when it comes to verticals within connections. But from my perspective, there's two principles that are always relevant when it comes to timber design. And what it's closely related to is understanding where we are when it comes to costs. So old technologies like concrete, they're at the very mature end of the S curve, and they're fully at the end. There's no real innovation that can actually save on cost there, well, on a relative sense. But when it comes to timber, we are on this S curve. We are at all timber in new mid-rise and taller building contexts. There is a big variation, and if you think about, we know sustainability is baked in, we know biophilia is baked in, but the cost is the big question mark, and that's why, from my perspective, it's the holy grail. If you can get the costs, get rid of a green premium, which is very possible, then you could get the triple bottom line, and then it's a no-brainer for projects. So one principle is solve it once, use it many times. So because this is so complex, if you think there's two paths to a design, one, when you say if you've got 100 hours of consultancy, you could spend that on one connection detail and scale it out 50 times and actually solve a lot of the things that I've mentioned before. That's one way of doing it. It's using leverage to its max. The other path is 100 consultancy hours across 50 connections, used 50 times. So obviously the second path will be more complex, and you're actually not going to be able to solve some of the multidisciplinary issues. So like always, keeping it simple, it's complex enough as it is. So keeping it simple is always advised. The second principle, and again, this could probably be applied to any sort of design, but it's solving for the bottleneck. So as an engineer, we might think that the bottleneck is all about our structural design calculations, but it's a bit like this little cartoon chart here. Imagine someone on the Titanic saying, "Deck chair arrangement working group, are you ready?" And everyone's arranging deck chairs. And this is just an analogy to say that sometimes the big picture is outside your immediate view. And that is the case when it comes to structural design. So you can spend a lot of time building a spreadsheet for the new Eurocode, but there could be a bigger picture where you could solve really quick by just, speaking to the supply chain up front, which connections best match their manufacturing capabilities and fire test data. Like I showed you before, Nathan, not trying to give Ash a big plug today, of course, but if you spoke to someone like that, you can get their expertise up front. But again, knowing the trade-offs as well. Also asking the installer, which will enable speed. All right, so that's a bit of the high level, I guess the Titanic version. Now we're going to start focusing on the structural design and connections. And the worked example we're looking at is inspired by the Lendlease 25 King Street. It's a beautiful post and beam commercial office building. You got your glazing on the outside with exposed facades. You've got primary, simply supported glulam beams with a 12-meter secondary span for CLT, which everything fits really nicely on a truck and designed from a DFMA point of view. So for the first worked example, we're going to look at two connection details, hopefully covering a bit of the theory, which I'm about to go through now as well. So let's call it a half flat and also a CLT floor to GL, a glulam beam connection. So firstly, when we get into it, so from a screw property point of view, this is what you're looking at with a screw. You've got the length, you've got the thread length, you've got the outer thread diameter, inner thread diameter, and the shank diameter. And all of these have different variations of different heads, threads, and so forth. So when it comes to screw design, covered in Eurocode is the most advanced method. It's Johansson's theory to actually determine the lateral loaded of the fastener. And the failure can be embedment failure within the timber or yielding failure of the fastener. So bringing that together, there are 6 different failure modes based on Johansson theory right here, and this is assuming single shear, as you can see here, and the modes A, B, C, D, E, and F. So I understand a little bit deeper. From a timber point of view, there's 3 properties that impact the design of the connections. So as you vary these, will impact the timber side of the failure mode. So for example, timber density, high density yields to improved connection performance. Like I mentioned before, if you have a connection detail with changing from spruce to a MGP 10 equivalent, and then the MGP 6 equivalent of like the the proprietary grades of Xland, for example, all of that will impact the design. Same with embedment strength and the timber thickness. So as you make it thicker or thinner, there's more capacity on the timber side, and then obviously the failure mode, with more capacity there, it's more likely to fail on the fastener side. Within the fastener, you've got withdrawal capacity, which is as if you're pulling the screw out. You've got the head pull through capacity, so that's with the head itself pulling through the timber. The tensile strength, and then the yield bending moment, so as if it's bending. Within the connection design, you've got partially threaded screws and fully threaded. So partially threaded offers stronger clamping force, so pulling timber components together, usually in a tension or reinforcement connection. Sorry, other way around. Then you got partially threaded clamping together, and fully threaded providing the reinforcement or connections under tension. So bring it all together. The 6 failure modes, the first 3 are on the timber side, so the thin timber or the thick timber or both timber members. And then the other failure modes, so D, E, and F, are within the screw. The first on the thin side or on the thick side, and on screw in both timber members. So they're the 6 failure modes. If you look further into connections, so the more you have a laterally loaded screw loaded in shear, acts quite different if you actually have an inclined screw. So an inclined screw will have more of an axial effect, and you're actually pulling using the threads to create the connection strength as well. So that's an option we'll go into in our connection detail design examples, where you could use a angled screw to actually use the threads in withdrawal. So there might be circumstances where you might angle the screw to get that extra capacity, and you can see here the difference between the normal force, the axial component, and then the design axial component dictates the design for inclined screws. Next, we'll go through as well is like screw properties. We're going to think about the service classes and the conditions. So service class 1 are in a dry environment, service class 2, covered exterior with occasional moisture exposure, or service class 3 with exposed exterior, and the new Eurocode opening up service class 4 as well. So that's a little bit about the theory. So next we're going to focus in on a connection design. So for our building, you can see here a standard commercial post and beam office building. We're going to be looking at grids G, H, and I to design some of our connection details in this location. So if we're thinking about the design of a floor-to-floor connection, the first thing we need to do is to work out what the forces are within the connection. So the way we can do this is we can obviously get the factorized loads from AS 1170, take that into a CLT toolbox calculator, which we're not covering today, which is a rectangular diaphragm design. You can have multiple panels adjacent to each other to work out the developed forces, and then you can actually take it into the floor-to-floor connection detail. So when choosing a floor-to-floor connection detail, there's a few things to think about. So you've got a few options. So a half lap. This is an example with good lateral transfer with interlocking panels. You might have less fasteners relative to the spline, but it does have extra machining because you do need to route out a portion of the rectangular panel in each time. And the other one is the fire might be more compromising for a thin panel, because you've got the joints. If you think about a exposed fire underneath, it might compromise the joint prematurely relative to the spine. The spine joint, it's very versatile. There's less material removal, but there are additional components. And then you've got a butt joint, which is the less machining from a manufacturing point of view. Very simple, but you basically butt the joints up together, but it's the weakest joint type and might require additional protection. So that said, we're going to now design our connection detail using, say, the ProHoltz Volume 2 to work out the joint forces. And we've got 11.39 kilonewtons in our floor-to-floor connection. All right, so this is CLT Toolbox. So we're going to be, that's our company, and we're going to be doing the connection details with. Thanks for sticking with us through all of that. So basically what I went through there is I've been just updating the screw based on the Timberlink screw and all the Rotherblast. So I went through the different screw families, chose the right screw, and then went through the calculations here from a geometry check as well. So that's incredibly embarrassing that I wasn't checking the right screen there in the app. So at the very end, we've got the shear capacity, and I'll do a new connection detail in a second, which should be able to help in that sense. So right now I'm changing the spacing and we've got this connection detail to work, but I will do a different connection detail which will catch everyone up. All right, so in the app, so again, going back here, assuming no one saw this, but we do have member design and connection design. So the second connection detail we were going to look at is a CLT floor to glulam beam connection. You click on your calculator and then you can add it to the scope of a certain project that you're working on. So for us, we're choosing a Wood Solutions webinar building. And then we'll fire up our connection. So I'll run through this again at the high level. So one of the things we spoke about earlier was the challenges of the different properties within the supply chain. So with our connection details, you've always got top view, section view in both directions as well. So top view, you can see the screws and spacing, say 4 meters, and you've got the alternative option to choose a 1 meter spacing. So the first thing we'll do is choose our CLT floor layout. You can always do manual input or choose your CLT floor, and you can see this working dynamically to build up your CLT. Secondly, your glulam supplier. In this instance, we can choose, say, Ash, and when you choose Ash, you've got all the grades that they supply, but also the sizes and the properties. So if we chose an Ash beam, say a big beam like that, you can see it working dynamically as well. So that'll be reading the different properties from the CLT and also the glulam supply chain. The third is the screw supply chain. So a little bit like before, which nobody unfortunately was watching. So you choose the screw supplier, and with that you can go through the screw families and work out the thread type, the head type, the diameter and lengths and the service class based on the screws. And as you change the screw supplier, you also get the differences within each one. So you can really quickly understand what's available within the screw supply chain as well. So just to spread some of the love, we'll go with the SPAC screw, partially threaded screw, and then choose our screw. So if we say a 10 mil by 400, you can see our connection detail right now populating. You can choose the spacings of the screw. So let's just say it's a 150 mil screw, and then this will then update the spacings of actually how our connection detail's working. And finally, you've got your forces. So if we chose, I think we had 14 kilonewtons, and then input the forces, and then you got the load data as well. So if you're moving through, you can look at the calculations here. So firstly, geometry checks as well. So you can see here, one of our geometries is working relative to the diameter of the screw. So we can go back and update that. And secondly, we've got the lateral capacity of the screw. So I was going through the theory earlier, but you've got the withdrawal of the timber, checks of the head pull-through capacity, tensile capacity of the screw, and then the actual capacity of the screw based on the minimum of the 3 above. And then following that, you go into the 6 failure modes of Johansson, the Johansson model. So embedment failure of the timber 1, embedment failure of the timber 2, joint embedment failure in timber 1 and 2, so the CLT and glulam below, and then the screw failure modes as well. So based on that, you can run through and see all the different capacities here. So out of the 6 failure modes, in this instance, with the CLT floor, with the glulam beam underneath, and the screw that we've been specified, the minimum lateral capacity that's governing is a double plastic failure in the screw at 5.5 kilonewtons per screw. So obviously you can change the screw and you could expect the screw capacity to change as well. And then you've got the total design capacity of the fastener as well, based on the spacing chosen. So that is how you design a connection detail of a glulam beam to CLT in CLT Toolbox. So you can see here it's not a black box. And one of the things that you can always do is change the orientation to get the benefits of incline screws, and then that'll start using the axial capacity of the screw. So you can see how that changed there from lateral capacity to the axial capacity to see how it's designed. So at the end of it, you That's a section, and then you can save the calculation and go on to the next connection detail. So I hope, Boris, that you're now looking at my PowerPoint.
Yes, I am.
Good stuff, mate. All right, so we've done two connections here. We've done a slab to beam and a floor to floor connection. Next, we're going to look at the design of lateral bracing. So looking at a dowel design, for example, and you can see here the external K bracing. They're always a feature of the design. So how do we actually design these things? So the first thing is connections may govern the member design. So as you do the analysis in an external platform, the next thing you can do is design the member check for tension and compression, and then design the dowel design itself, and just see what is the governing factor in this instance. So with us, you got the load analysis as your first step. Work out the forces, usually on the closer to the ground floor for the maximum tension and compression. So for our example, you can see here we've got maximum compression force of 175 kilonewtons. So we can go back to our project page where we're doing our calculations for this example. Go to a member check, design the member, and open it up. So one of the things about we always really have these dynamic views, so you can see how the cross section's working from a force point of view. So for us, we're choosing a diagonal brace like that. I think it was a 5650 millimeters. And as you change between design codes, all of the design and duration of loading and everything like that will update. So for us, let's just say we're using A1720 for the design, and 5 seconds for, say, a wind loading. So choosing your GLT, and again, you can choose your supplier availability or manual input. So 205 by 205, something quite simple. Next, you got your design actions. So for the forces, because we're not focusing on member design today, it's just to prove the principle of for completeness. As you turn off your bending moment and shear force, you'll just be left with your checks that's left over. So for us, at 170 kilonewton compression load, and you can see right now we're working. Similar below, you can go through your design data and work out your K factors for your member design. So for us, we had a 205 by 205 member working, and next we're going to design a dowel. But the completeness will go through all the checks. So you can see in the design checks, you'll have your compression parallel to grain, your combined actions, detailed calculation of your stability factor based on it being for a column. All right, so that's for the member part. Next, we're going to design a dowel for the same check. So if you go to connections, if you click out large dowels and bolts, you've got the ability for internal plates and external plates for your design, and single shear as well. So for us, we're doing wood, steel, wood to conceal the connection as best we can. Going to our project. Loading up our dowel design connection. So this again is one of the tricky parts from a structural design point of view, and you run into the same challenges as before. So you can see here you've got a cross section in both directions of our member that we're designing for. You can do a compression load with a negative, so it's in compression, which was 165 kilonewtons in compression for one direction of the bracing, or in tension as well. So you can configure the loads accordingly. For our design codes, you can see here Eurocode, new Eurocode, A1720, and the New Zealand design standard as well. You've got your spacing parameters. So as you input that can be the thing that actually governs the design. So if you go to N4, 4 rows, for example, you'll see below that our geometry checks aren't working. Next is choosing your middle steel plate. So the steel plate itself governing the design. And then again, the members itself. So if we go back to our ASH member, we added 205 and 205. You'll see pretty quickly that it's actually all out of the page. So with this, you can actually go back to the actual design, try and configure it to get working appropriately to really consolidate the design. So I'm just going to make the depth here thick enough to fit both dowels in this instance. Next, you got the fastener properties, so the bolt types and fastener grades, and then our design data as well. So if you go through here, you can run through all the checks again. So dimension checks based on the geometry. So we are working in this instance. So it's relative to the dowels and the steel plate and the timber and edge distances all come together. And then our design parameters, and then our strength design as well. So as you go through the different design methods, so the actual laterally loaded dowel is working in a similar sense to the Hansen yield model with a similar failure or the similar timber and steel properties that we covered at the start of this webinar. So a few of the extra things, it does include brittle failure modes and things like that when you do the dowel design here. So that's the fourth connection detail that we've covered here. And again, I might go. You can configure it accordingly to get it 3x3 and improve the actual connection detail as best you can. So now we are governing in terms of our design based on the forces that have been inputted into the design. So 165 kilonewtons was the force we inputted there. So we got our large dowel and bolt connection working, but you can see here the actual size of the timber member was governing connections instead of actually governing in the member itself. So it's one of those things. So also the geometry checks is one of the things that might govern the design. So if we go back here, we might have time for one more connection detail. So we've covered right now laterally loaded screw, which is different to looking at laterally loaded, but also an incline screw taking into account the axially loaded screw. Now we're going to look at a completely different connection detail, which is a reinforced beam notch, for example. So a lot of times might happen in a design process, you might need a beam penetration or something like that to actually have a deeper beam, which is unexpected in the detailed design phase. And you might need to find a height in a different mechanism in a different way. And sometimes a beam notch is one way of doing that, for example. All right, so if we go back to the app here, again, you can go into our calculators. So obviously all these calculators are meant to cover all the certain random scenarios that pop up when you're designing buildings. So in this instance, you can see our timber failure modes. For this instance, we can go our beam notch, add it to our webinar, and then we can open up our beam notch check. So we are doing a relatively fast version just to get a good coverage of different connection details. So yeah, what you're looking at here again is the dynamic view. You've got the column underneath, looking at from the bottom, and then the beam there, or section view of the column and the beam, and then the side view as well in the other direction. So for us, if we chose, say, an ash beam, you can update the actual beam size here and how much it's notched in member. So for a beam of the building of the type we're looking at, it might be a bigger section like that. Your supporting column, if you look at the bottom view, it's not really matching up. So let's just say if we've got a 450 by 450 column, so that's now matching up with the size of the member itself. And if you look at the section view, we can start actually designing the size of our notch. So you can see the small notch here. So H effective is 700, so 105 millimeters there. And you can start designing the length of the notch here if there is a slanted notch connection like that. So that's actually just detailing the notch, and you can see it in all the different views to make sure we actually are covering what the notch looks like. The design methodologies again, so Eurocode in that instance. Input your forces based on the notch, and then you can see the check. So you can see we're failing here in bending stress. One of the options we can always do is add the ability for screw reinforcement. So that's, as you can see, it's only based on the new Eurocode, which actually enables this option. So as you choose the screw reinforcement, a little bit like before, you can choose your screw supplier, there'll be a filtered version of just the fully threaded screws that might be applicable for your reinforcement, and the number of screws. So if you look back at our connection detail, you can see we've got 3 reinforcing screws at this notch in both directions, and we can then do the actual design in this instance. So you can see right now we're working, albeit I put in the 100 kilonewtons, and you can actually optimize the design a little bit further. And always not being a black box, you can actually see in detail all the checks. So in here, it's the shear base check based on the new Eurocode, and you can hunt down the calculation routines, and it'll do the same if you're based on the current Eurocode geometry checks, and then the reinforcement design based on the actual capacity of the screw. So that's it's quite a detailed check. And then at the very end, and we'll stop in a second to go for questions, but what we always have is the ability to actually print our reports at the end. So this will take a few seconds to actually load up the report, but you can see the roadmap that we're following. Next is the ability to export and import based on bulk CSV files. So if you're using a deliverable or an ETABS or something like that, you'll be able to do the design. So this will take about 15 seconds to actually do the to load up properly. So whilst we're doing that, we're about to end the webinar anyway. Here we go. So there's the detail. You can see all the calculations of the PDF report that we've actually produced. And then you can, of course, export it. And then you've got a design report based on all the checks that we've done in this webinar so far. So that's about it. So what we covered today is a lot of theory on connections. I don't know what you were looking at, everyone. Apologies about the start, but I think we recovered hopefully by the end, Boris. So appreciate everyone, and thank you for some questions.
Yeah, no, look, yeah, thanks so much, Adam. I think it was a really good overview in terms of, I suppose, the key takeouts is that when engineers are doing design in particular, it won't all be found in 1720 Part 1, and need to look at some other, like the Eurocode 5. But Adam, just from the work that you've done with engineers, and I suppose I'll take the first question if you wouldn't mind. How do you work in terms of that certification perspective? Are the engineers, like if they're using Eurocode 5, in terms of that, how's that accepted here in Australia?
Yeah. So that's always going to be a performance-based design. So obviously it's outside of A1720 whenever you're using Eurocode. So that means being performance-based design, you're obviously relying on engineering judgment. So it's up to the structural engineer to determine and make the call that is the most appropriate design method to actually design the building properly, because that is, I guess, the intent of any design, is design buildings as safely and efficiently as possible. And sometimes that is just the best method. And so, yeah, it's performance-based design, and you need to go through get the performance-based design brief and everything like that as well.
Yeah.
And that's just what it is. From the outset, CLT is not in A1720. Aspects of beam and column design aren't either, or some aspects aren't. So at this stage, it is just outside of the Aussie code.
Yeah, look, I suppose I can add to that as well, Adam, is that there is work that's being done, particularly in that CLT side, into the design with CLT. So there is work being done to try and incorporate that in the 1720 Part 1. So there's work being undertaken now. So that's something to keep an eye on. I've got a couple of questions that did come through. One of the questions was, can you deal with hardwood dowels as part of the connections? Is that available in the software?
Yeah, not at this stage. It's one of those things, like if enough people ask for it, we'll eventually get that in. We are speaking to some more specifically dowel laminated timber producers, or hardwood dowel timber producers who feed into DLT products. So yeah, it's one of those things at some stage we'll get it in, but not today. We've got bolts and steel dowels.
Yeah. Another question was about when using 1720 Part 1, do you sort of add in anything in relation to brittle failure calcs from other models?
Yeah, it's a good question. I think that was that was Lisa. So we keep them separate. So AS1720 is purely AS1720, what's available. So you just see when you choose that method, it's just basic tables to form the design. And then when you change to new Eurocode or the ASMZ 1720, if you change to that, then you'll have all the new brittle failure modes populate. So, and that's one of those things. It's not on us at CLT Toolbox to make the call on how to best combine different methods. We just provide the different method and a good tooling to actually do the calculations for you. And then it's of course up to the likes of Boris, like you mentioned before. I think you're working with Lisa and a lot of people to actually do some of the research to see what is the most appropriate combination of everything for Australia. But I guess what we do is to be able to actually quickly swap between methods means you're on the conservative side. You can find out if you're on the conservative side very quickly, which is, or sometimes unnecessarily too conservative as well, is might be another extreme you might find out if it's based on just 1720. So we just provide the options and then the education, because you do have the engineering judgment, hence the education is really important to pair with the design methods.
Yeah, and look, there is obviously with 1720 Part 1, it's been a while since it's gone through an update, and so there is work happening both in the connection side of things as well as looking at design of our members like CLT, but that will take a little bit of time. But I think the other question that was raised was about the inclined screws. Obviously 1720 doesn't cover that, but you just use the Eurocode approach for the design of inclined screws.
Yep. Yeah, that's right. And, not every screw as well, not just some screws aren't meant to be for inclined as well. So that's like where, based on the ETAs, we filter out that as well if it's not appropriate for inclined screws. And same for reinforcing screws. Just because it's fully threaded doesn't mean it's always available. So there's a lot that goes into, I guess, every screw in the testing to enable that, which is a whole separate beast to the actual code compliance as well. So there's a lot of moving parts there.
Yeah, and there was another question that's come through more about with the connections and moisture effects in terms of the design or behaviour of connections in products like cross-laminated timber from a moisture perspective. Maybe just, I'm not familiar with that. Is there any sort of design approaches that are used in your software, or is it anything generic that's done along those lines?
Yep. Yeah. So I guess the first principle is always to just protect it. Or if it's indoor and if it's all internal, you've always got the ability to specify the screw, which has corrosion protection and all that sort of stuff. So you can specify the screw from that point of view. But if you're designing for a dry environment, it's Jeff Morell's 4Ds of durability. That's another great webinar from Wood Solutions, and that first things first is just like protect the timber and the connection from moisture at all costs. But if you need to, you can specify a screw or the timber as well to be treated as a belts and braces approach as well.
Look, and I suppose 1720 also has that K factor for moisture change in there as well. That could be sort of adjusted in terms of the capacities of the screws, which I'm sure would be under your 1720 model, and I'm sure Eurocode does the same thing.
Yeah.
All right.
Totally.
All right, Adam, look, we'll leave it there. So we're coming to the end of the webinar. Look, sorry I had that little bit of an issue at the beginning, but you've picked it up well at the end, and you've taken us through and showing us the I suppose the power of software these days, and the ability to use that, engineers to use it for design purposes. So thanks.
Thanks so much, Boris. Thanks so much, everybody.
Okay. So just to close up the webinar. As I mentioned at the beginning, that our webinars are recorded, so the webinar will be made available within a week online, so you can access that through the Wood Solutions website. And our next month's webinar on the 6th of May is the making of Taruna and Yanduit structures or buildings. And our presenters will be available on the 6th of May at 11 o'clock. So look, I'd like to thank you all for attending today's webinar, and we hope you can join us next month as well. So all the best. Thanks, everyone.